last session for today, and the next speaker, actually two speakers, who are also our co-organizers, are Dr. Zhou from Professor Hong Kong Park's group and Dr. Ilya Esterlis from Professor Eugene Dambler's group, and they will tell us their most recent research on bilayer Wigner crystals in van der Waals heterostructures. So as in previous sessions, the talk itself will be 30 minutes, followed by 10 minutes discussions. I will give a 5 minutes warning. I guess you will go first, right?
Yes, that's right.
Okay, the stage is all yours, please.
Okay. Yeah, thank you very much for the introduction. So Ilya and I will present our joint work on study of bilayer Wigner crystals in van der Waals heterostructures. Because Mansour and Shahar has given such an excellent introduction to Wigner crystal, I will just be very brief here. So in an electron system, when the potential energy dominates over the kinetic energy, we can have a variety of very interesting electron correlated phase. One of the earliest predicted such correlated phase is actually a Wigner crystal phase, where the electrons form a regular lattice structure to minimize their potential energy, just like atoms in normal crystals. The most interesting aspect about these Wigner crystals is that they can exhibit a variety of different phase transitions. To understand this, we can introduce a parameter gamma, which is simply the ratio of the average potential energy to the average kinetic energy per electron. And we can say that Wigner crystal only happens when gamma is much larger than 1. So now if we heat up the system, for example, we can increase the thermal energy, thermal kinetic energy of the electron, which leads to the thermal melting of the Wigner crystal, just like how you melt a classical crystal. What's even more interesting is that there is also a phase transition even at 0 temperature. So if we look at a 2D system where the interparticle distance is on average R, the potential energy scales with R, 1 over R, but the kinetic energy scales with 1 over R squared. So if we calculate gamma, then we find that gamma will be linearly proportional to R. So this means that if we go from a dense layer to a dilute layer, going from small r to large R, we can induce a phase transition from the liquid to the crystal phase even at 0 temperature. So it's convenient to introduce a parameter Rs at 0 temperature, and we find the critical phase boundary usually happens at around the Rs value of 20 to 40. What's even more intriguing about these quantum phase transition is that near the phase boundary, it has been predicted by Boris Spivak and also Stephen Kivelson that there could be interesting emulsion phases, and there could be also interesting magnetic ordering near the phase transition. However, as we learned from Mansour and Shahar's talk, it's extremely challenging to realize these Wigner crystals, particularly in this quantum regime. The difficulty in realizing Wigner crystal in semiconductors has to do with the small effective mass of electrons in semiconductors. For example, in gallium arsenide, the effective mass is so small that the critical density is only on the order of 10 to the 9th per square centimeter. And this is problematic because if we have similar number of disorders in the system, the disorder will just destroy the long-range order of the Wigner crystal. So how can we actually overcome this challenge? And in the past, people have been relying on applying a large magnetic field or other confinement potentials so that you can suppress the kinetic energy of the electrons and stabilize this Wigner crystal phase. For example, under a strong magnetic field, you force the electrons into cyclotron orbitals, which quench their kinetic energy. So you see this very nice insulating feature near the fractional quantum Hall regime as done back in the 1990s. However, the application of this magnetic field also introduced other ground states, such as these fractional quantum Hall liquids. Well, it's very interesting to study such liquid to solid phase transitions, you can see that such a system will deviate from Wigner's original vision. Another way to quench or suppress the electron kinetic energy is to create a Maury potential, as we heard from Jie and Allen. So this is a new way to confine the electrons at a local Maury potential and reduce their kinetic energy. So not only can you observe these multi-insulating states, but also other types of electron ordered solid state at the fractional feedings of the Maury lattice. What's different from Wigner's original idea here, however, is that such electron ordered states is not only stable by the interparticle repulsion, but also you have to rely on this underlying potential. So as a result, they will exhibit different symmetry properties compared with original Wigner crystal. For example, you have discrete symmetry breaking rather than a continuous symmetry breaking in the original picture. So this can lead to different phase transition properties. And as we heard from Mansoor's talk, it's extremely challenging to realize Wigner crystal without a zero magnetic field. So far, the only signature of Wigner crystallization is perhaps for the holes in the gallium arsenide system. So in our experiment, we actually want to try to realize Wigner crystals without applying a magnetic field or a Maury potential. The material system we use from is actually transition metal dichalcogenides, as we learned from Jie and Allen. These are 2D semiconductors, and in monolayer forms, they have a direct band gap. And you can combine them with other 2D materials to form so-called van der Waals heterostructures, so while maintaining this atomically sharp interface. What makes these materials particularly promising for hosting Wigner crystal is that because of the reduced dimensionality, they feature weak Coulomb screening and therefore strong Coulomb interactions. At the same time, the charge carriers have relatively large effective mass. So this means that the kinetic energy is rather small. So if we just plug in the material parameter, we find that Wigner crystal, the critical density for such crystallization is actually pretty high, on the order of 10 to the 11th per square centimeter. Furthermore, in our experiment, we actually also create a bilayer system to further stabilize the Wigner crystal. This was actually predicted by an early theoretical paper back in the 1990s. So if we consider two monolayer Wigner crystals and introduce interlayer coupling, such interlayer coupling can enhance their potential energy and stabilize the Wigner crystal. So we want to actually leverage this effect to further stabilize the Wigner crystal. Not only these materials are promising for realizing Wigner crystals, but they also provide a convenient way to study the electrical properties of the material. In particular, you can use an optical tool to study their electrical properties. For example, if we build a field effect transistor using MOSC2 at 0 voltage when the material is intrinsic, if we measure their photoluminescence, we see strong emission from the neutral exciton. It's an electron hole pair, and also weak emission from the charged exciton. This is the exciton bound to some residual charges in the system. Now, if I change the gate voltage and change the Fermi level, as soon as I turn on the in-plane conductance in the 2D material, I find that there is a dramatic change in their optical properties. In particular, once the Fermi level reaches the conduction or the valence band, what you can see is that the neutral exciton diminishes and there is an enhancement in the charged exciton emission. You can actually also observe such dramatic change in the reflectance or the absorption of the material. Such correlation between their electrical properties and optical properties means that we can actually just measure their optical response and tell whether the material is conductive or insulating. So this actually provides a rather nice way to probe their properties, because we can just use a laser to probe as a mesoscopic tool to study their properties within a diffraction limited spot. rather than doing a global transport measurements. Okay, so in our device, in order to realize this bilayer structure, we start with 2 monolayers of MOIC2 that's separated by a very thin layer of HBN. And in order to avoid Mori effects in our system, we choose these 2 layers to have the same crystallographic orientation. So we do not need to worry about them to the first order. We also add top and bottom gate and the gate dielectric so that we can control the carrier density in both of these 2 layers. So initially, if we do not apply any voltage, you see that this bilayer emission spectrum resembles the monolayer case, where you see mainly from emission from the neutral exciton. And indeed, in fact, these 2 layers have the same exciton energy. That's why we are only observing single exciton peak. Now, if I apply a gate voltage on one gate, this is to dope one layer, but keep the other layer intrinsic, you see a reduction in the neutral exciton and the enhancement in the charged exciton. And of course, if I apply gate voltage on both gates, I can dope both layers so the material becomes conductive. I completely suppress the emission from the neutral exciton. So by doing this kind of measurements as a function of top and bottom gate voltage, I can create a 2D charge map of how the system's charge state change as a function of top and bottom gate voltage. In here, so when we observe strong signal, these bright signals from the neutral exciton reflectance, we know that the material is intrinsic. So both layers are intrinsic. On the other hand, if we apply positive voltage on both gates, now I dope both layers with electrons, so I see very weak neutral exciton response in this corner. So this shows that we have an excellent control over the charge states of the individual layers in the system. However, nothing is very surprising here. Now, if we zoom into this small region represented by the dashed line and do a fine voltage scan, we see something quite surprising. Okay, so this is a fine scan of the 2D map. As you can see, even when we apply 2 positive voltage onto both gates, we see that there is actually strong neutral exciton reflectance and also photoluminescence, even when both layers are doped with electrons. And because a high neutral exciton emission means the material is insulating, this suggests that somehow the bilayer system behave as if they are in an insulating state, even when both layers are doped electrons. In fact, we observe a series of such features denoted as 1, 2, 3, and 4 in these maps. So if we look at the condition for such insulating states more carefully, because the carrier density you induce is simply proportional to the gate voltage divided by the gate thickness, such straight lines will correspond to a constant density ratio between the top and bottom layer. And we find that these density ratios are 1:1, 4:1, 7:1, and 1:4 in our experiments. Another interesting feature is that if we move along this constant density ratio and increasing the total density, we see the insulating states begin to disappear as well. So this is quite surprising to us. So to further show that we are indeed seeing some insulating states along these features, we can also look at the line width of the exciton. Because if you introduce any free carriers, these free carriers can scatter exciton, and this leads to the broadening of the exciton line width. So if these features are indeed insulating, we would expect them to have a narrower line width compared with other normal features. And indeed, that's what we observe in our experiments. So to understand such insulating states formed when both layers are doped with electrons, we attribute these to the formation of bilayer Wigner crystals. Once again, in the theoretical paper, it has been predicted that you can stabilize a bilayer Wigner crystal by introducing interlayer coupling. And as you can imagine, such stabilization should only happen when you can stagger two triangular lattices in a commensurate fashion. So Ilya will explain more of this, but we can find that the commensurate stacking of two triangular lattices happens at the density ratios of 1:1, 3:1, 4:1, and 7:1. So our experimental observations of these particular density ratios are therefore a telltale sign of this bilayer Wignall crystal formation. Okay, so as I mentioned, one of the most interesting thing of our Wignall crystal is that they can exhibit both quantum and classical phase transition. So in our experiments, we want to also probe these two phase transitions. In order to do that, we need to characterize the density dependence of the Wignall crystal. And we actually need to disentangle its density dependence from the intrinsic materials density dependence. So in order to do that, we introduce a parameter called delta. In this very naive picture, if there's no interaction between the two layers, the total emission from the bilayer system should be the simple sum of these two individual monolayers. So we should have a delta equals 0. However, if there's any interaction-driven insulating states, the emission of the neutral exciton will be enhanced. So we'll have a delta larger than 0, sorry. So we can actually use delta larger than 0 as a proxy for the formation of Wignall crystal. If we calculate that, we find that indeed along these features, we see a large positive value for the delta. Once again, this shows the formation of Wignall crystal. And if we want to construct a phase diagram, we can just repeat this process for different temperatures. And if we only focus on this 1:1 density ratio, we can plot the value of delta as a function of both density and the temperature. So because delta larger than 0, we can use it as a proxy for the Wignall crystallization. So we can say the phase boundary is given by the value of delta equals 0. So we end up having a dome-shaped structure in this NT phase diagram. What's remarkable about this is that at the base temperature, if we calculate the Fermi energy of the system, this is proportional to the kinetic energy in 2D, we find that the Fermi energy is much larger than the thermokinetic energy KBT. So this means that the system is already in the quantum regime, and here we are inducing a quantum phase transition into the liquid phase. And this also explains why we are seeing decreasing density as a function of increasing temperature, because we add additional kinetic energy by heating up the system. On the other hand, at this very low density regime, the critical density increases as a function of temperature because this is due to the thermal melting of the Wignall crystal. So from such analysis, we can actually map out a whole phase diagram of the Wignall crystal in both classical regime and also in the quantum regime. And this also qualitatively agree with our expectation. We can do more quantitative analysis, for example, by calculating the value of gamma as a function of density and temperature, and assume that this liquid and solid phase has a constant gamma value. And if we pick the boundary based on the critical density, we find that it actually agrees with our experiments reasonably well. And we can also look at the bound fluctuation and use the Lindemann criteria to estimate the melting of the Wignall crystal. And Ilya will explain more of this. Yeah. And also, although these two estimate phase diagram shows the qualitative agreement, it's actually quite surprising that we are having a very large density
Are you guys going to do that soon?
For the Wignall crystal. Okay, so now I will switch over to Ilya, and he will describe more of the stabilization of the bilayer structures.
Huh?
So, do you, I see, I don't have video. Are you guys able to hear me okay? Okay, so I
Yes.
Okay, I'm not able to turn on my video for some reason. My cursor has disappeared. Okay, so as long as you can hear me. Okay, so thanks very much, Yo. So at this stage, I thought I would maybe just take a step back and discuss a bit more about the bilayer system from a theory perspective. So let me just start with an kind of idealized schematic phase diagram of a two-dimensional electron gas bilayer. And for simplicity, let me just start with the case of equal densities in each layer. So in this system, we have, as you described, we have two dimensionless parameters. We have the usual RS, which is the ratio of typical, there we go, thank you. Right, we have the usual RS, which is the ratio of the typical interparticle distance to the Bohr radius, and the ratio of the layer separation D to the Bohr radius. And so, okay, so firstly, the two extreme ends of this phase diagram are easy to understand. So when D equals infinity, meaning the layers are decoupled, the system is, we know, liquid for small rs and forms a triangular lattice Wigner crystal at large rs, with the transition occurring at a value of rs equal roughly to 30. And this value has been estimated, for instance, by Monte Carlo techniques, for example, in this kind of seminal work by Tanatar and Separately from '89. And now the other easy limit is D equals 0. In this case, we simply have a monolayer with twice the density, and hence again, a triangular lattice at large RS, but now with the lattice constant smaller by a factor of √2, and correspondingly a critical RS larger by a factor of √2. So here RS is defined with respect to the density of a single layer. Now, if we turn on a weak interlayer coupling, the bilayer can in fact lower its Coulomb energy by simply staggering the layers relative to one another, and this enhances the stability of the crystal to higher density or smaller RS. And in fact, this critical RS has been predicted to go down by as much as 30%. And this was first estimated by in this PRL that Yo mentioned from the early 90s by Sverkovsky and collaborators. And now, okay, let me just be clear. So this phase diagram is, of course, much richer and more intricate than this simple sketch here suggests. So for instance, you see that I write Wigner crystals, plural here. And that's because, as you can imagine, in going from this kind of staggered triangular structure to this single layer Wigner crystal with decreasing interlayer separation, there will in fact be a sequence of structural transitions that interpolates, between these structures. And so in fact, this series of structural transitions was worked out in the classical limit in this paper of Goldoni and Peters from the late 90s. But the main thing I want to kind of stress about this phase diagram is that weakly coupling two-dimensional electron gas monolayers is beneficial for Wigner crystallization. Okay, so now in the current experiment, to give you a sense of the numbers, if one uses just the dielectric constant and effective mass of molybdenum diselenide, the TMD, under consideration, and the experimental values of the interlayer separation, we find that this parameter D over AB is roughly 2. And we can also estimate that the system is crystalline roughly in the range of RS from 6 to 16, with this upper limit just corresponding to the sort of lowest reliable densities. And now from the data, the experimental data, kind of in relation to the previous slide, one might infer a schematic phase diagram more similar to what I show here. So in fact, the thing to emphasize here is that you see that the tendency towards Wigner crystallization in the bilayer appears to be rather dramatically enhanced. So the critical RS is something like 6 relative as compared to roughly 20 from these early theoretical estimates. Now, of course, I don't want to mislead you. So we only have in this experiment one cut in this phase diagram when D over AB is roughly 2, but the point here is not to suggest anything quantitative about the shape of this curve, but just to draw your attention to the fact that there appears to be a rather significant enhancement towards crystallization in this system. Okay, so to better understand the crystal structure that occurs in the system, and in particular for an analysis of the case with unequal densities, let me focus now just on the low density or classical regime of the system. So in this case, one just ignores the kinetic energy of the electron, so the Bohr radius drops out, and the system is just described by a single dimensionless parameter called here eta, which is defined as the product of the interlayer separation and the square root of the particle density. Okay, and in the current experiments, this parameter takes on values roughly in the range 0.1 to 0.2. Okay, so now let me analyze the system starting from the case of weak interlayer coupling. So in this case, we start from a picture of weakly coupled triangular lattices, and we can just ask for which density ratios will these lattices be commensurate with one another, and hence where we might expect some enhanced stability of this bilayer. And we can simply construct these lattices as follows. So first of all, clearly 1-to-1 ratio is commensurate, so let's just skip that. The next thing we can do is just to consider neighbors of a particular point. So let's, for example, pick in this 1,3 case, this red point at the origin. And you see that we can consider its next nearest neighbors, which are the, sorry, for some reason my cursor is not working, but you see there's a triangle formed from the red dots, and you can check that the edge lengths of that triangle are precisely square root of 3 times the lattice constant of the triangular lattice defined by the black dots. So these two lattices will have density ratios, one of 1 to 3. Okay, the next thing you can do is consider next nearest neighbors. These form triangles of side length 2a and hence correspond to density ratios of 1 to 4. And similarly, further neighbors correspond to 1 to 7 and so on. And more generally, and of course, to minimize the Coulomb energy, one simply has to stagger these lattices relative to one another. And so more generally, the sequence of numbers is generated by simply considering the set of distances on the triangular lattice, which can be written in this way shown here, n squared plus m squared plus n times n, where n and m are integers. And the first few numbers of this sequence are shown here. And you'll recall that these are precisely, these first few are the ratios that were showing up in the experiment. And so you'll notice that I have here 3, which was not explicitly mentioned in the experiment, the ratio 1 to 3, but actually just very recently, Yo and his collaborators, they have data that suggest indeed there is a feature at a ratio of 1 to 3 when they cool the system down to lower temperatures. So if there are questions about this, perhaps Yo can speak to that a little bit later. Okay, so let me now just contrast this with the case of strong interlayer coupling or small eta. So remember, eta is defined in this way, d times square root of density. And in this case, we can just start from the eta equals 0 limit, in which case we have a single Wigner crystal with twice the density. And then the effect of a small non-zero interlayer separation is simply to determine how the particles in the two layers are distributed on this underlying triangular lattice. And the main point I want to make here is just that in addition to the weak coupling ratios I mentioned on the previous slide, one can in fact form structures for various ratios. So just as an example, here's a configuration for a 1 to 2 ratio. You can similarly construct 1 to 5 and various other ones. And so given the absence of all these other ratios in the experiment, this sort of analysis suggests that really the system under consideration appears to be in the sort of weak interlayer coupling regime where the important feature is commensurability between triangular lattices. Okay, so conceivably there are of course many interesting probes of such a bilayer crystal, but let me just comment on one, which is the phonon spectrum. And
Ilya,
yes.
Sorry to interrupt you. You have 5 more minutes.
Okay, perfect. Thank you. Yeah, so let me start just for the phonon spectrum for a monolayer Wigner crystal along a path in the triangular lattice Brillouin zone shown here at the top of the figure. So there are 2 gapless branches. There's a longitudinal plasmon branch with a root Q dispersion and transverse branch that's linearly dispersing. And now upon weakly coupling the layers, the root Q and linear and Q branches persist, but now the system will in addition possess 2 optical branches. And in fact, in the weak coupling regime, the optical frequency has a simple characteristic exponential dependence on the interlayer coupling eta, with alpha here being a dimensionless number that varies as the square root of the density ratio in the layers. Okay, and so this optical phonon mode is really a unique fingerprint of such a bilayer crystal, and I think its observation would be rather compelling evidence for this picture that we're proposing. Okay, so let me conclude by mentioning what I think to us was one of the most surprising or puzzling features of the system, which is that this bilayer crystal appears to really be somehow remarkably stable. So for instance, the critical density RS is significantly lower, or the critical density is much higher than what had been theoretically expected. So in fact, the critical density is about an order of magnitude larger than what one might have expected. And also, if one tries to just do a simple kind of Lindemann criterion analysis of the melting, one finds a Lindemann parameter that is significantly higher than its conventional value. So let me just remind you that the Lindemann criterion is just a simple criterion to estimate the melting temperature of a crystal, and it just states that the melting occurs when the RMS fluctuations of the phonons exceed some fraction of the lattice constant, that fraction is called the Lindemann parameter, and it turns out, a sort of semi-universal value. So for a monolayer crystal, it's found to take on roughly the value shown here, 0.25. But using the density for our system, we estimate a Lindemann parameter that's roughly a factor of 2 larger. So this is further indication that somehow this bilayer has a significantly enhanced stability. And so maybe I can also just mention one possible resolution here, and that's just to realize that this exciton probe that's being utilized is really somehow more directly a probe of the quasi-particle spectrum of the underlying electronic system. And as such, what we deem an insulating phase might be more accurately thought of as an incompressible regime of the system. And so this kind of unusually high density regime may in fact just correspond to some sort of broad fluctuation regime or pseudo-gap regime of the system. And so to flesh this out, one would really like a more direct probe of the underlying crystal structure, for instance, by looking at Umklapp scattering of excitons in this crystal background. And this is this probe will in fact be discussed, this sort of probe will be discussed in more detail in a talk tomorrow by Tomasz Smolenski and Pavel Dolgirov. So let me just advertise that. That's happening tomorrow at 12:40. But okay, nevertheless, I think it will be very interesting to try to understand why these states appear to be so robust. Okay, so with that, let me just turn it back over to Yo for concluding remarks.
Okay, yeah, so such system, I think we think that it opens up a lot of very interesting directions to further probe the properties of the Wigner crystal. For example, we can look at their nonlinear transport behavior, and also because there is special phonon structure, we may look at their AC transport. And as Ilya mentioned, you can think about these excitons as very tightly bound particles, so they can serve as a local probe to probe this Wigner crystallization where the interparticle distance is larger than the exciton radius. In addition, such Wigner crystals can also have collective motion and interesting magnetic ordering. In these transition metal dichalcogenides, we can actually use an optical probe to probe possible magnetization. So that's also one very interesting directions. So Ilya, could you go to the next slides? Yeah, so with that said, we would like to acknowledge all the people who contributed to the work, especially Hong Kong and Eugene and Philip and Misha Lukin.
Thanks.
Okay, thank you, you and Ilya, for the wonderful talk and very interesting studies. Please raise up your hands if you have questions. Professor Moglu, sorry for pronouncing it wrong. Yeah, please go ahead.
Yeah. Thanks. Thank you very much, Ilya, and you for the talk. I have actually 2 questions. So the first one, Ilya, to you concerning this ratio that you quoted, which is D over AB of about 2. But if I understood correctly, the separation is about 1 nanometers. So is it really that, I mean, it seems to me like with 1 nanometer, this weak interlayer interactions is not exactly justified. I mean, I'm basically thinking about, let's say, if you have electrons separated by, say, 10 nanometers, and if the interlayer separation is 1 nanometer, so it seems to me like inter versus intralayer interaction would be comparable.
So indeed, so that's in fact, one kind of puzzle still that remains for us. So I mean, this sort of analysis doesn't take into account, for instance, the dielectric properties of the intermediate HBN and so on. But yeah, I mean, it's true that if one kind of uses naively just the numbers in the experiment, it's more suggestive of a strong coupling regime. But in that regime, it's just very hard to see how these particular ratios are special in any way. So yeah, it's to us at least, it still remains an open question. Why the system is living in this weak coupling regime when the naive parameters sort of suggest otherwise. Yes.
Okay. So thank you. So also a question to you. So basically, these features, for example, in 1.1, where you see that the exciton oscillator strength remains high as compared to other sort of neighboring filling factors. So I presume this has a sort of corresponding signature on the attractive polar line. Is that correct? Do you also see that the attractive polaron remains weak for 1:1 ratio, for equal ratio of the two lines?
Yes, exactly. That's, let me just maybe share my screen again. Yeah, because I think I have yeah. So we actually indeed see that along these features, let me see, it should be inside here. Okay, yeah. So this one is actually correspond to the attractive polaron or the charged exciton. As you can see, along these features, you indeed observe that the attractive polaron or the charged exciton have a much lower intensity compared with the other ratios. So this is exactly what you said. So yeah, so you're absolutely right.
Thanks.
Do we have more questions? We have time for a couple more questions. Professor Dasama, please.
Yeah, I had actually two questions. One is that I guess the questions are theoretical, but since the theory connects with experiment is the claim, it's a question for the experiments also. So I'm slightly puzzled by this, this phonon picture with an optical phonon gap opening up. Even if I had no Wigner crystal, I'll have exactly the same picture. If there is slightest bit of tunneling between the two layers, I'll have an acoustic plasmon and an optical plasmon with a mass. And they will have even the same dispersion. So suppose I do an experiment and I see some optical experiment and see some modes with a gap, which is, I mean, how do I know it's a phonon and it's not a plasmon? This is not just a regular bilayer electron gas?
Yeah, so that's a good point. So indeed, yeah, you're saying just the small interlayer coupling would tend to gap out.
Let's use the word tunneling. Let's be careful because people use these words randomly. Coupling to me is an interaction. I'm just talking about, imagine if there was no tunneling, then fine. But there may be a little tunneling. You may do not know if the experiment has no tunneling, right?
Yes.
So then there'll be a gap in the optical plasmon. You know, if you have two layers of electron gas, you have an acoustic plasmon and an optical plasmon. And then a gap opens up if there is any tunneling. And then the spectrum would look very much like your phonon spectrum, right?
Yes, I agree. Yeah, sorry, I misspoke. Yeah, so I agree. I think one thing, so I'm not sure if it would be the same in the scenario you're describing, but in this case where it's, optical, for the optical phonons I was describing, there's a very particular dependence of this optical phonon frequency on this eta parameter that I defined. So for instance, for a fixed layer separation, if one could measure it, you could see that it should decay exponentially.
I get what you're saying. What you're saying, one has to do detailed work, quantitative work to see what the dispersion looks like, quantity dependence. I do accept that. I mean, but the problem is that, that sort of thing, if you have a theory, there is always confirmation bias in the experiment, and it's very hard to kind of distinguish these things, varying D and varying those things. It's much easier if it's just Q dependence or something. You see what I'm saying? In the same experiment, they can do that then. But I see what you're saying, and I accept that. And my second question was something that I guess I did not follow something since I haven't seen the paper.
Sorry, Shankar, can I sort of?
Sure, Eugene, go ahead.
No, just to comment. Yeah, just to comment. But let's say in the plasmon scenario, right, there are no transverse phonons, right? Because I think what's special for the lattice is that it's not just longitudinal phonons, but also transverse phonons.
Right. So
therefore, if you see transverse phonons.
Yeah, if experiment really sees, shear modes, transverse phonons, then there is no discussion because you have seen something that a liquid cannot have, a solid can have. But typically, optical experiments really cannot tell you those things. Optical experiment will see a mode with some frequency, or maybe it can. That's why I said my question is both for experiment and theory. Maybe I missed something that experimentally, the experiment is so precise, you can distinguish. Experimentally, you see a mode. How do you know whether it's an optical plasmon or an optical phonon? I mean, it's a question, it's not a comment. I'm not an experimentalist.
Oh, Shankar, it sounds like a perfect question to discuss during the kind of 5 o'clock discussion section.
Let me ask a quick question on the other thing. So what allows this system to be treated as just an electron gas. Alan McDonald gave a wonderful talk and told us about how important lattice is and so on. And I come from the electron gas background. I'm learning all this language by reading Alan's papers. And now you go back to something I understand very well, which is a much simpler problem. What allows that here? Why can you treat this system as two simple electron layers?
Well, so here the nominal twist angle is 0. So there's no moire potential.
There is no flat band physics at all.
Yeah, yeah.
Okay, all right, so maybe then it's okay. I would have to think about it, but at least that's the answer. All right, thanks.
And the system is sufficiently dilute that probably this is a.
I get it. Yeah. Mm-hmm.
Okay, do we have more questions?
And I don't. I'm happy.
So I don't see more questions from the audience. I have a last questions for the experimentalist and also the theorist. Do you expect, I may have missed that part from the talk, do you expect something can happen for the double graphene system separated by HBM, like the structures that Philip has been working on?
Yeah, I think if we look at the effective mass of the graphene, it's a little bit smaller than compared with the PMDs. So you may expect the Wignall crystallization to happen at lower density. However, there are a variety of other interesting physics, like Philip probe, like the condensate phase. That's also under magnetic field. Maybe Philip wants to say something.
That's probably a good discussion point at 5 o'clock, I think. I have a lot of questions as well. I don't know why people, I think not only us, I think many people actually try to see that this kind of low phase of the correlated state in the probably not in the single layer graphene, but bilayer graphene is still kind of doable experiments. I don't know what is the expectation. Maybe this is worth to revisit, but yeah. So far, there's no experimental report as far as I know, but interesting point to discuss.
Just a quick comment. So I think that the graphene systems might as well show the very beautiful Wignall crystal physics. I think that the main difference between the graphene system and this one is that we can actually probe this Wignall crystalline phase using optically, because of the attach and then using this beautiful work. And then because of the nature of this probe, it is actually semi-local mesoscale by nature. So there is some differences, but the thing is that these are certainly some very interesting points to discuss.
Okay, great. Thank you. So